Today, let's talk about the properties of interior lighting. And let's start with the chapter 5, the patterns of brightness. And basically, the idea here is that there are certain real simple patterns that come out of the lighting fixtures that we tend to use in our interior environments, artificial light fixtures. And the light fixtures themselves are generally not the kind of star of the show. It's the pattern of light that you see coming out of the light fixture that's most important, typically. And that's why we so frequently use recessed lighting. And that recessed lighting can have different angles of light coming out of it from really a narrow spot to a quite wide flood. But then you also see other kinds of light distribution patterns. Again, a lot depends on the equipment that you're using and also what you're hoping to light. If you want the fixture itself to be kind of the star, or if you want what you're trying to light to be more important. So let's take a look at a couple of examples. Here's a recessed light, or actually I guess it's not totally recessed because we're getting a little bit of a lens flare on this. It's actually a computer rendering. But it is a narrow light source. You can see that it's just kind of making a small blob on the floor. And this is a very typical kind of arrangement that we use all the time. Recessed lighting that we use to either spotlight a spot on the floor or to highlight some object from a distance. You use a narrowly focused light that can throw light a long way. And this sort of situation can arise even with not fixtures that are not recessed. In this case, this is a fixture dangling, pendant mounted over a table. And the light is coming out of the light fixture in a very controlled manner. You can actually see the seats that are in the foreground here are not actually all that well lit. And the table itself is well lit, that the distribution of light, the angle actually matches the diameter of the table so that the table is fully and well lit, but the light doesn't spill. It's a very precise kind of arrangement. Or in this corridor, I got a kick out of this corridor because normally you try to find a fixture that has a distribution angle, the angle that the light comes out of the fixture, that is designed within that space to produce really an even lighting along the floor. In fact, if you think of an egress corridor, that's probably ideal. You don't want uneven illumination in an egress corridor. But what they've done here is they've chosen a light fixture, and I'm going to give them the credit of thinking that it's intentional. They've chosen a light fixture with a somewhat more narrow distribution angle, and what that gets you is this kind of rhythm of dots on the floor, these big blobs of light, which actually is kind of nice. It's a long corridor, and it's kind of an interesting effect, especially in a monochromatic kind of space. Also, I do think that there is a rhythm that's set up with the kind of angle of light, the kind of slash that crawls up the wall and onto the ceiling. And I think that is part of the design as well. Finally, this was a nice decision to use a square recessed light fixture. I think we often just use, well, whatever's available on Revit, right? But in fact, the aesthetics of that square is kind of nice. I think it actually goes with the square section profile or proportion of this corridor. And nowadays, with using LED light sources, there's no reason that the luminaire aperture needs to be round. Round, I think, made more sense when you had incandescent light sources and even compact fluorescent. But with LEDs are square themselves and can be arranged in any pattern. So I think it makes more sense. This is the MIT Chapel by Eliel Saarinen, and this is again an interesting space we've looked at a couple of times. It has uplighting, lighting that comes from this kind of trough along the perimeter of the space that is it basically is grazing the wall. I believe there's a lot of fill light in this particular photo. I couldn't find a good one that showed just the fill light. But I also believe that there's a reflecting pool around this building, and that light in the reflecting pool reflects up from the underside of the wall, in addition to being augmented with electric lighting. And we do tend to forget that you can have lighting in the floor. It doesn't always work, because the issue is going to be you're going to see that light source, because we do tend to look down a lot more than we tend to look up. So, but there are certain situations where that uplighting can be very handy, and you can use fixtures that have good glare control, that have a good cutoff angle. This image actually, I'm not sure if they've photoshopped it or what, but it does have a kind of glow around the light sources, which is not really what you want. But if you're trying to light, say, an arch or an unusual ceiling construction, this is really the best way to do that. The sort of light source or light distribution pattern that we're most familiar with, or at least that's most showy, is this omnidirectional light fixture, light distribution. And omnidirectional means all directions, and that's basically if you think about it, a bare bulb, a bare lamp, or a sort of fixture like a chandelier, which is again meant to kind of show off itself. You're supposed to look at the chandelier, and because it's bright, we tend to look right at it. We tend to be drawn to those bright surfaces, and it creates a certain, I don't know, festivity almost. In the book, the author uses the term sparkle, and there's something kind of fun and, I don't know, jolly about the word sparkle. It isn't always the greatest illumination on its own. Like, if you look at the plates and the table, there's a lot of stuff going on here that actually is frankly maybe a little too much. There are too many reflections. But on its augmented with downlighting or other types of decorative lighting, I think sparkle has a great place in our lighting tool bag. Then there are what we call up-down lights. And these are lights which throw light up and down. And actually, I scanned this right out of the book. This happens to be Gary Gordon's office. And in fact, my desk is kind of in the back there. And the funny thing about this kind of lighting is that it can be mounted in a number of different situations. In this case, the lighting is mounted hanging from the ceiling. And the effect here is that the uplight lights the underside of the floor structure above, and that can create a real nice sense of volume and spaciousness, especially if the ceiling is clean of most of the other crap that you see up in our ceilings, like ductwork. The downlighting provides adequate lighting for the work surface, and in this case, believe it or not, they're actually drafting tables and layout tables. This is a very old photo that's in the book. Anyway, other sorts of lighting distribution that we have talked about briefly, but now we're going to look at even more. Grazing lighting is the type of lighting which washes down a wall, but washes down it at a very close angle. So you really emphasize the materials of the wall. Wall washing is basically the same distribution, but from a slightly greater distance. It does not show off the materials quite as well, but it does produce kind of an evenly illuminated wall from top to bottom. And here's an example of a wall wash. And again, to emphasize the difference, it's just the distance from the wall. You could use the exact same fixtures and get a grazing light or a wall wash effect, or almost the same fixtures. With LED light fixtures, you do have to choose one fixture that has the angle of distribution that is different. You can't aim them quite as well. Usually in the old days, you could aim the light fixtures a little more effectively because they had lamps in them. Speaking of lamps, here's another approach to wall washing. This is from track-mounted lighting. As you can see, it is bare lamps. This is probably what you would see in a gallery setting. In fact, I'm guessing that's what this is because it's an awfully blank wall with a lot of light on it. But the advantage of this is that it's imminently or completely flexible. You can have multiple paintings on this wall and aim a light or two at each one, or you can just have the entire wall kind of evenly illuminated. Now, the reality is that most lighting design, most spaces, are going to have layers. They're going to have a little bit of downlighting with a wide angle. They're going to have some downlighting with a narrow angle. They're going to have some wall washing, and they're going to have some grazing lights. So every space that you look at, in all likelihood, is going to have some variety, and that's what lends richness to the space. So in this case, if you look by the mirror, there's kind of a light behind the mirror. That's one effect. Then there's these little pin lights on the bench seat that have a narrow light distribution. And then there are recessed cans up in the ceiling that have a wider distribution. So you really get a variety of effects, and I think that some more subtle designs are going to have those layering that we're talking about here. And here's just another example, a retail store. Retail stores tend to just have massive amounts of lighting. And if you look at the cabinets on the walls that are displaying, I don't know, look like pendants, you will see that there's a light inside that cabinet that is facing the front of those displays. There's also lighting inside the cabinet in the center of the room and along the perimeter of the room. There are some downlights on the chairs in the back of the room. And then there's some wall washing, or really grazing from the looks of it, around the perimeter of the room to give it a sense of spaciousness. And finally, there's the kind of kidney-shaped, I don't know what it is, thing up in the ceiling. It's a lighting cove of some sort. And that is also another lighting layer. So here you could just tally up the lighting layers, each one with its own kind of unique structure. So now let's talk about the evil of glare. Glare is the enemy of good lighting. And there's a number of reasons. As mentioned, our eyes do tend to go to the brightest spot in our visual field. And if it does that and you don't want that, it can be distracting. It can also be tiring. All those bright light sources can really cause your iris to, or your pupil to expand and contract all the time. And that just tires you out. If you have relatively even and unchanging illumination, or slowly changing illumination, your eye just won't get tired as much. So I think we now need to delve into some terminology. The one term that I have mentioned from the start is that we don't call them bulbs anymore. We're going to have to call them lamps, and I will try to be consistent about that. The bulb is the glass or plastic part of a lamp that's essentially a diffuser. In modern lighting, in LED lighting, in the old days, it contained a vacuum, and the vacuum prevented the tungsten filament from burning out too fast. And a luminaire is a complete artificial lighting unit. Equipment or fixture are also words that we use for that. And I think if you look in the glossary of our textbook, which you should, you will see a very similar sort of description. Glare is the perception of luminance in the visual field greater than the level of adaptation. So typically it's about 3 times the adjacent luminance level. And what that means is that your eyes are adapted to a darker light level, and some bright light source enters your visual field that your eyes just aren't ready for. And an example of that would be oncoming headlights. Your eyes are adapted to the dark, and then suddenly a level of light comes into the visual field that's way beyond what your eyes are ready for. Those headlights in the middle of the day wouldn't cause you a problem at all. So you might say, wait, what does luminance mean? Well, let's now talk about the breakdown of the different lighting terminology. And here is the diagram I'm going to use to hopefully explain this. I have another diagram later on that it's a little complicated, but luminous flux is the total amount of light from a lamp in all directions if you just add it up. And I always think of like a sprinkler in the backyard. If the sprinkler is going and spreading light all over your yard, the luminous flux is akin to the total amount of water coming out of the sprinkler. So it's just any which direction. You have a bare bulb hanging in the middle of a room. all the light in all directions. If you add that up, those little lighting pieces of light, then that's luminous flux. Luminous intensity is light energy in a given direction. Now, that's typically measured in candela. The luminous flux is measured in lumens. Now, illuminance is the amount of light landing on a surface. We can measure that in foot candles or lux, and that's usually the thing we're calculating for. So, for example, in a classroom, decent light level, the standard light level is probably about 25 foot candles. And you can measure that. You can go install your lighting, aim it if you need to, and then take out a light meter and say, oh, we've got 30 foot candles. Uh-oh, we need to change something. You can also calculate it very precisely using manufacturer's data. Luminance is the amount of light leaving a surface, and that's in candela per square meter. And that is essentially reflected light. Okay, so illuminance and luminance sound very similar. You'd think they could come up with words that are more distinct, but sadly they don't. So when we talk about glare, it's luminance. It's typically reflected light that is greater than the level of your adaptation. Now, you might say, doesn't illuminance make sense if the headlights are shining in your eyes? Well, yes, it does, but this is how they define it, so I can't fight City Hall on this one. So here are some horrible images that show you the brightness of headlights. And again, when your eyes are adapted to the dark part of your visual field, the brightest thing in your visual field might be these taillights. Suddenly the headlights come in and they are so much brighter that they are producing so much more light. Your eyes aren't ready for it and they cause discomfort. Or even in an architectural space like this, what's nice is you can see the little burn in the photo here. This is an up-down fixture. I think they probably should have had more down and less up in this case. Or here, another great photo of an exhibition hall. And what I like about this, we have all taken photos like this with a dirty camera lens and it's off at an angle, but also the light sources hanging in this area are just not great for this particular kind of displays. A lot of displays actually have little roofs on them, a lot of these kind of convention displays, for this very reason that convention lighting is basically just hideous, just too many bright fixtures in your field of view. Now, there is an ad campaign out there for Pixel, which takes advantage of this too. Here, let's play. Doesn't that make you want to buy a Pixel 3? Well, all right, maybe not. Anyway, so let's talk about how do we control glare. Well, the biggest thing is that you, as the interior designer, are kind of designing your spaces for different activities, so you know where people are and what they're looking at, more or less. You kind of set the stage, and so if you take that into account and you think about where in their visual field there are risks of glare, then you can start to think, well, okay, I can have lighting outside of that area. That's the kind of worst. And typically that is a 45-degree cone of vision, kind of 45 degrees off your line of sight. Now, of course, people move and they look up and down, so it is assumed that that line of sight is horizontal. I do think that it is sometimes worth considering that people do move their heads around. For example, in a gallery, people are going to be looking around because it's a place that's meant for that. So shielding the light source is really critical. But one of the things to consider, first of all, is that the brightness of a light source, the surface brightness, is really important. And different light sources have different levels of surface brightness. So, for example, an old incandescent light might have had a brightness level of approximately 150 candelas, per square inch, whereas an old fluorescent tube would have had only 5 candelas per square inch. So, a pretty significant difference. So, just by using fluorescent tubes instead of incandescent lamps, you immediately decrease the risk of glare because the tubes themselves just aren't that bright. Now, you also have the possibility for shielding the light sources, and we have seen that in a number of fixtures that we've looked at on our little tours around campus. The shield angle is really important. That 45-degree cutoff angle is going to save you from glare for the most part. And it's actually not rocket science to design these. It's lighting science, and it's just a matter of coming up with a baffling device, a shielding device that's going to block the light and also look good. Now, another little trick that you can do is you can take a light source that has too much surface brightness and just put a diffuser around the entire light source. And you see this with, big globe decorative light fixtures. That globe is there not just to protect the light source, but also to spread the light out. You can also have, instead of a globe-shaped thing around your light source, you can have a diffuser that is a horizontal piece. And this is very common in, say, an elevator where they just have a sheet of plexi, basically, that's semi-transparent, and translucent is the right word. It lets some light through, but it lets it through in a manner which diffuses it. Other materials which are common as diffusers are things like frosted glass and different types of acrylic. Now, the fixture itself, the luminaire, can be designed to throw light in a particular direction and shield at the same time. This is an older style fixture. It looks like a metal halide lamp to me. And you'll notice the shape of the light fixture. It has these reflectors. And if you look up into a fixture when it's not on, you'll see these aluminum reflectors that basically are shaped in such a manner the parabola forces the light to come and reflect all in the down direction. So these parabolic downlights are great for getting very precise control of your light direction, and you'll find that you can get downlights in a number of different angles. So what about in a space? Let's just take a look at a kind of realistic situation. If you're in an office, if you're trying to design an office, how do you know where the tables are going to be? Most offices are pretty adjustable. So what you're going to want to do is have some control of the brightness at the fixture by diffusing it or baffling it in some way. And then you're going to want to think about the angles that people are working at. Now, fortunately, typical offices are going to have what are called heads-up tasks or heads-down tasks, where you're just kind of working at your desk. So the lighting can be controlled. The angles get worse when people stand up, as you might imagine. But fortunately, in an office, nobody's allowed to stand up. And you also want to think about orientation of the light fixture to the desk, both kind of front to back and left to right. The upshot of these diagrams is that it's really hard to control lighting unless you have fixed furniture. The glare is such an issue that choosing luminaires that have a high degree of glare control is your best strategy. Now, let's talk about adaptation, since that's another one of those words that we have discussed. And we have done an in-class exercise on adaptation. But basically, the upshot of adaptation is as you get older, it's slower, but what it is, I guess what the definition is your eye adjusts to have better perception at different light levels. So when it's darker in a space, your pupil opens up and lets in more light, and your rod system takes predominance over the cone system, and that allows you greater low light perception. It does, unfortunately, make glare more persistent as you get older because your eyes can't adapt as fast. I think in our in-class demonstration, your eyes all adapted much more quickly than my eyes. So anyway, other things that you can do is you can control the angle of the light on glass surfaces. For example, if you're lighting a painting that has a glass frame around it, make sure you do a little bit of calculation to figure out where the reflecting angles are going to be. Glass is highly reflective. Those of you who have glass cell phones, which we all do, you can get these really bright spots on them, even with treatment on the glass. Most phones are smudgy because of people, running their hands across them after eating, cheese steak sandwiches. And so the amount of surface brightness, this is called a veiling reflection because it's like a veil covering your eyes, or in this case, your glass. It's really hard to control on glass. It's just so reflective. Okay, let's talk about the color of light now. And we did talk earlier in the previous lecture about, well, what is light? It's radiation, and we can only see a little bit of it. Lucky us, we just get this pretty rainbow, but we don't really see infrared or ultraviolet all that well. One thing to really kind of knock into your head, and I'm sure this is natural for you, but when you mix pigments, for example, paint, they are what are called subtractive. Basically, you when you mix them together, if you mix everything together enough, you get black or at least mushy brown. Every kid kind of does that. They dump all the paint into one thing and swirl it around, and you end up with a muck. Lighting is the opposite. It's additive. So you add the primary colors of light together, and you get white. And the thing to think about here is the color of light, the range of light coming out of the light source has a huge effect. And then there's the color of the object themselves. So for example, sunlight has all wavelengths of light, and that's why we perceive it as white, because it has a little bit of red and a little bit of green and a little bit of blue, and all of a sudden you've got a white light because they add together. If you shine pure blue light on multicolored objects, the only one that's going to look blue is the blue one, because the wavelength that material reflects is matching the wavelength of light that's in the light source. All the other objects will appear gray. They won't. This diagram actually kind of makes it appear as if they don't appear at all, that they disappear. That is not true. An example of that is parking lot lighting, old parking lot lighting. If it had that yellowish kind of hue to it, that is low pressure sodium. It's notorious for really basically being just yellow light. So unless you happen to have a mustard yellow car, maybe a Pacer or something like that, every other car would just appear gray. So then there's the reflective properties of objects. And again, I think it's important to recognize that all objects that we see, almost all objects that we see, really have a mix of colors. And what I like about this diagram is I like lettuce, I like tomatoes, and I like butter. And I think it's a nice diagram. Plus, we're familiar with tomatoes being red, but they are red of varying kind of wavelengths. There is some yellow in there, there is some green in there, and of course the variety of the tomato makes a little bit of difference. Butter, I don't think it has quite that much red, but maybe. But it does require you really studying these objects to see the real colors that are in there. Now, people don't perceive colors in the same way. It varies from person to person, and more dramatically, it varies by gender. Unfortunately, or fortunately, depending on how you look at it, male and female humans just don't perceive color as precisely. It's a physiological thing. Men in general, although not always, just don't have the sophisticated level of cone receptors that females do, and that's why females are better able to discern more subtleties in color. It's just a physiological concern. As mentioned, the incidence of color blindness in men is 16 times greater than in women. So obviously there's some some difference. But what about bees, you might say? How do bees see things? Well, bees actually, interestingly, can see violet, past violet, into ultraviolet. They apparently don't see orange, which is very interesting because a lot of flowers are in that color range. But the question is, why can they see ultraviolet? What's the advantage? And it's hard to say, but I do know that moths, for example, have basically a very boring pattern, a lot of moths on their back. But if you look at them under ultraviolet light or infrared, I can't remember which, these patterns often appear that are quite dramatic and beautiful, but cannot be seen by human eyes. Presumably, they can be seen by other moths who are like, wow, that is an impressive pattern. So each animal adapts to their environment a little bit differently. Doesn't really help us when we're doing lighting design unless you're planning to do lighting design for a bee. And I've also mentioned several times, because I like dogs, that dogs, they do not perceive the full spectrum of color. And again, this is a physiological thing. They just don't have red receptors. It doesn't mean that they can't see red objects. They just see them as gray or yellow. And why would they need so much color? I don't honestly know. And it is interesting that the things that dogs like to eat are fairly muted in color. But I wonder if there is some defense mechanism where you can be a really bright color that gets you attention from other animals of your species, but the dogs don't notice you. Now, when we talk about how things look under different light sources, we use a scale called the Color Rendering Index. This is a scale of 1 to 100 that measures how well colors appear under a given light source, and daylighting is the standard. So, as mentioned, daylighting is how our eyes are fully and most healthfully adapted to see other colors, our skin color, and all objects look more natural in that color rendering of daylight. So if you want to get your ideal, you're going to have to try to match that daylighting effect. And it just has to do with the kind of spectrum of colors that a light source emits. Now, it is related to another thing called color temperature, which we'll talk about in a minute, and also light level. Light level and color temperature all have an effect on color rendering. And if you think of, say, a Best Buy, which is always my example for these things, the light level is very high. So the color temperature of the light source needs to be correspondingly high in order for colors to appear natural. If you had a warm white light, but it was as bright as it is in Best Buy, 75 to 100 foot candles, things would just look weird. They would look reddish and strange. So anyway, let's go and take a look at some of these light sources. First of all, this is daylight. Now, daylight can vary depending on where you are, latitude and longitude, and of course cloud cover and, smog. So, but this is kind of our goal, a light source that has this spectral distribution. Now, here's a cool white fluorescent, and you can see that there are kind of these spikes in the cool white fluorescent spectral distribution chart. Those spikes are going to cause all sorts of problems with color rendering. The biggest one being that if you happen to be wearing that shade of green, for example, a wavelength of whatever that is, 420 nanometers, your shirt is going to be very bold only in that color. It will be muted in all other colors. And if you just compare the charts, you can see that the power is much less overall in all wavelengths. It kind of peaks in that kind of yellowish range. An incandescent light has a very smooth curve, and that's why they appear to be so much more natural. Basically, incandescent lamps burn stuff to produce light, and so does natural daylight. So natural daylight is coming from the sun, which is burning whatever it's burning, hydrogen. So LED light sources are also quite variable. they do tend, I believe, to be a little smoother, and they are wildly varied by manufacturer. It's a relatively new technology, so they haven't totally got it down yet. But for color rendering, LEDs have gotten pretty good. They are probably not as good as incandescent, but they have other advantages that have made them basically come to replace incandescence. Now, the other feature of light that we have to talk about is color temperature. And it's measured in degrees Kelvin, so it actually is based on the kind of universal temperature scale, and it is based on something called a black body radiator. Now, what exactly is that? I've never quite understood that, but it's some object made of material X that is black apparently, and as they heat it up, the temperature rises. Sooner or later, it begins to emit color. And at 800 degrees Kelvin, it emits red. And then at 5,000 degrees Kelvin, it emits white, and it becomes sort of more blue at 6,000. And I tend to think of like a fire when you're sitting by the campfire. Sometimes there's little red flames that are licking up, and those are warmer color temperature. But the really hot fire where you're cooking your potatoes, that tends to be almost bluish if you've got a good hot fire. And I like this chart because it does kind of have some indicators that people are familiar with. Candlelight is going to be a very warm color temperature. Sunlight at midday is going to be cooler. And then finally, an overcast sky that does tend to cast a bluer light. And that's going to be a cooler color temperature. So also, when you have a space that is brightly illuminated or not so brightly illuminated, you're going to want to tune the color temperature so that objects appear natural. And again, in a Best Buy situation, you're going to need a cooler color temperature. But if you're sitting by a romantic dinner table, you're going to want a much warmer color temperature. That little electric candle or a real candle, that's going to want to have a 2,000 or 2,500 degree Kelvin color temperature. And the corresponding level in foot candles, anything below 5 foot candles is not a lot of light. Okay, you aren't going to be doing anything in that level of light unless you're looking at a phone which has its own light source. Now, when you get anything above 100, it's really, really bright. So you're going to want to be careful. At 50 foot candles, I'm going to guess Best Buy is probably in the 75 foot candle range. And you can see here that the color temperatures that are going to look natural, well, probably if you stay in the middle of the curve, you're looking at about 5,000 degrees Kelvin. Now, the Illuminating Engineering Society of North America, IESNA, publishes guidelines for a lot of these things. These are not sort of like, oh, I didn't know that. These are things which are standard and are based on our physiology. And so they published illuminance targets in foot candles for a number of different spaces. What's interesting is that they publish them by age group. So, for example, if you're designing a college dormitory, you're going to want to use the under 25 numbers, assuming there's no other code constraints. So, for example, if you're in a passageway, 2 foot candles is probably fine. In a reading study area, say at a, library table or a lounge table or something like that, 25 foot candles is fine. Do notice how those numbers go up over the age of 65. So if you're designing a dormitory for senior citizens, suddenly the light levels become vastly higher, 4 times the level as for under 25. And again, this is it's our physiology, but you do have to be aware and really think through your clientele and the sort of end user and the person operating a facility that you're designing, and think about who are these people, and how they perceive the space around them. So just to round it all up, luminaires have a range of light output kind of directional profiles, which we can control and we can choose. That's our job. Color temperature is the appearance of the light itself, whereas color rendering is how objects appear under that light source. And I will reiterate, I do believe that objects don't really have color so much as they have reflective properties. So just looking at the color alone when you're deciding what kind of lighting to have on the fancy materials you choose is not enough. You need to think about, well, how is that material going to look under different light sources and different kind of characteristics of light?